Hey students, today we're going to be talking about what a limit is, where they can be useful, and how we can find them using graphs and tables in algebra. On your copy of this, where I have a blank box for the check your understanding part, you're going to see that you have some links here to Khan Academy. Those are the assignments that you should be able to do after completing this, kind of going through this video. First thing we're going to look at is its graph. I'd like you to pause this video and to write down as much as you can about things that you notice about this graph. Okay, please pause now. Some of the things that I notice about this graph, and I'm coming at this with about 20 more years of experience doing calculus than you have, so I'm going to have a lot more experience noticing things about graphs. I notice that this is a rational function and that we have some asymptotes going on. I don't know why I'm writing this over here instead of in the part that I labeled for observations, but that's okay. So we've got some asymptotes here. I've got some kind of a horizontal asymptote, and that talks about the end behavior of a graph. As this graph approaches infinity in the x direction, it's being limited by this horizontal asymptote. I've also got a couple of different vertical asymptotes. I've got one, somewhere on the negative side and one somewhere on the positive side. And what's happening as I get close to these x values, my y values are unbounded, or they're approaching some kind of infinite value. There are lots of other things that you might notice about this, but those are the ones that are going to relate to limits today. I'd also like you to notice that we didn't actually talk about what limits were yet. Here's another scenario. So on the first page we had a graph, and here we're going to talk about some kind of reasoning. Specifically, we're talking about a fictional world where things are mathematically perfect. And we're going to stand, let's say some distance, 10 feet, 20 feet from the wall. It doesn't really matter. And what we're going to do is take jumps, and each time we're going to get halfway to the wall. And mathematically, what happens is we start at 20. We jump, our first jump takes us to 10 feet, and then to 5 feet away, and then to 2.5 feet away, and then to 1.25 feet away, and so forth. And what ends up happening here is that mathematically there's no way we can ever actually reach the wall. We know in reality this is not the case. At some point you're going to get so close that you can not physically get any closer, but mathematically we're approaching some distance from the wall. And you might notice that as the numbers get smaller and smaller, we're approaching zero. This is the second thing that's talking about a limit instead of some defined value at a specific point. In our first example, we had asymptotes that were getting close to those values, and if we could go out to infinity, we would actually get there. But we can't really do that mathematically or in reality. Here we have a case where if you could take an infinite number of jumps, you would eventually get to 0 feet. So we have the same idea that we can get real close to this value, but functionally speaking, in a world of math, we can't do that. Let's look at a third scenario. All right, so we've got 0.1, we've got 0.11, and then 0.111, and then 0.11111. If we were to keep going with this, you'd eventually end up getting to 0.1 repeating. And mathematically, this gets kind of interesting. Because here we're starting with 0.1, which is 1/10. And then 0.11, so we're looking at 11 over 100ths. We're looking at 0.111, so it's 111 over 1,000ths. And then we've got 1,111 over 10,000. And what I'd like you to do is to take a minute and see if you can find what fraction this is getting closer and closer to. Please pause and then come back. Okay, you might have noticed that decimal-wise, we're definitely getting closer to 0.1 repeating. And what that really means for us is 1/9, which is really weird. So we're starting out at 1/10. And we're gradually getting closer and closer and closer until we actually get to 1/9. Once again, we have this idea that we can get closer to a number without actually getting there mathematically, but getting real close otherwise. This, again, is this idea of a limit. And for our fourth scenario, we're going to go into the world of physics. This is going to ask us to recall some stuff that we've done in the past in Algebra 2 and in pre-calculus, talking about modeling the height of something that's falling off a cliff. And I'm going to use, I don't know, I'll use feet just because the numbers will be easier to work with. So we know that the height of some object is going to be equal to negative 16 t squared plus whatever that original height was. For the sake of having numbers that we can work with here, I'm just going to decide that that height is going to be 1,000. So that's a really, really tall cliff. But you can choose whatever height that you'd like, and you can deal with the idea that some of these values might be negative, and that would mean that we're below ground, but that's okay. There's a link here if you need to go review what it means to find an average rate of change. Take a minute or two to do that now if you don't recall what that is. Otherwise, I'm going to pause here for you and let you calculate these on your own. I'm going to put the answers in here and come back in a minute. Okay, so I've calculated these values for us. I use the average rate of change, which we know is just the slope between these two endpoints. So in each of these cases, this would be our x1 and x2. And the y values we'd have to plug in to our function to get. The values that I got go from negative 80 meters per second down to negative 64.08 meters per second. And one of the things that hopefully you notice is that we start out going down real fast. And then very quickly, it seems like we're approaching some kind of a really specific number. So by draw a picture to represent what we're doing, what I'd like us to think about is not drawing a cliff and throwing, I don't know, a rock off of it, but rather think about the graph here. So we know this is a parabola. It's going to be a parabola that has a vertex at the y-axis. It's just going to keep going down like that. And let's claim that this is going to be 2 comma whatever that is. And here is going to be 3 comma whatever that is. At each of these points, we're finding the slope between the two endpoints of that interval. And one of the cool things that goes on here is that we're taking this interval and we're cutting it in half. And we're finding a new slope. And then we're cutting not even in half, but finding a fifth of that. And then getting closer and closer and closer until if I were to zoom in to this point that we're getting real close to, where we have 2 seconds and then 2.005 seconds. That slope is so close to basically going through 1 point that we're approaching something that we're going to call an instantaneous rate of change. And what an instantaneous rate of change is a place on a graph where we can calculate what the slope would be if we could go through just that 1 point, finding the slope instead of 2. Hopefully we realize that if you tried to do the slope, let's say from 2 to 2, we'd end up dividing by 0, so we can't actually calculate that. Thinking about this in terms of this new idea of limits, we can talk about, well, the slope appears to be getting real close to negative 64 as these 2 points get close together. And the last of our scenarios is going to be another function. This one's going to be purely algebraic instead of thinking about this in terms of physics. Based on this, we should have an idea of some of its features. Hopefully we realize that this is going to be a rational function and should look roughly like this. You don't really need to know much more than that at this point, but you should know this looks like this. If I begin to fill out this table, I'm going to pause so that you can try to get these values, and I will plug them in. And one of the things that I'd like you to notice here, and again, you check your answers, make sure that we're on the same page, is that as we are on the right side of this graph, we are starting at, let's say 4 is here. We are moving to the left, and our y values are going up and up and up. So you might say that as our x values approach 0, our y values are approaching, and you might guess that if we get closer and closer and closer, we'd be approaching infinity. In Algebra 2 and Pre-Calculus, we talked about this a lot in terms of graph behavior and end behavior, and talking about this type of notation, whereas x approaches a number, y approaches infinity in this case. We're going to talk about this with regards to calculus notation and limits in our next video.